Welcome to the Graphical Corrosion channel. My name is Marcell Zade. I'm a researcher in the field of corrosion and protection of materials. An introduction to this channel is available on video number E28. Chapter 2, Section 10. Thermodynamics of electrochemical reactions. Graphical representation of electrochemical equilibrium. Pourbaix diagrams. The reference is Fundamentals of Electrochemical Corrosion, ASM International. Origin of Pourbaix diagrams. The equilibrium electrochemistry of an element in aqueous solution can be represented graphically using the coordinates of E' and pH, equilibrium half cell, and acidity or alkalinity of the medium, respectively. Video number E4, Chapter 1, Section 4 is available on this channel for more information about E', E', and E double prime. These graphical representations, known as Pourbaix diagrams, are essentially phase diagrams from which the conditions for thermodynamic stability of a single aqueous phase or equilibrium of this phase with one or more solid phases, generally pure metal, metal oxides, and metal hydroxides, may be determined. Who is Marcel Pourbaix? Dr. Marcel Pourbaix, 1904 to 1998, was a Belgian chemist who greatly contributed to studies on corrosion. His biggest achievement is the derivation of potential pH diagrams, better known as Pourbaix diagrams. In 1966, Pergamon Press published Pourbaix's Atlas of Electrochemical Equilibria in Aqueous Solutions. This atlas contains electrode potential pH diagrams for many elements and a critical analysis of the data on which the diagrams are based. Iron-water Pourbaix diagrams are seen in this page. Left, iron oxides and hydroxides. Right, iron hydroxides. Certainties and uncertainties of Pourbaix diagrams. 1. Pourbaix diagrams are thermodynamic charts derived using the Nernst equation. 2. These are phase diagrams or maps that represent the conditions for thermodynamic stability of a single aqueous phase, also equilibrium of this phase with one or more solid phases may be determined. 3. Any point on a Pourbaix diagram indicates the most thermodynamically stable form of a metal at a given electrode potential and pH. 4. The aqueous phase is characterized by the activities of simple and/or complex metal ions and the pH that is established by adding acid or base that ideally has no other effect. 5. The objective of these diagrams is to provide a large amount of information in a convenient form for quick reference. 6. There may be uncertainties as to exactly which phase is the stable one at a given pH and potential. 7. Also, different phases may appear depending on the immediate past sequence of pH and potential changes, and although such phases are not truly equilibrium phases, they may persist and, for practical purposes, represent the steady state of the system. How to establish a predetermined electrode potential. The experimental arrangement shown in this figure is used to establish a predetermined potential in which the functions of the components are as the following. A. The aqueous solution of controlled pH. This solution may contain dissolved oxygen, or the container may be closed and an inert gas such as nitrogen gas or helium gas bubbled through the solution to remove the oxygen present from contact with air. B. The working electrode or WE, which is the electrode under study. C. The auxiliary or counter electrode, usually platinum, against which the potential of the working electrode is established. D. The reference electrode against whose known half-cell potential the electrode potential of the WE or working electrode is measured. E. The electrometer or high impedance voltmeter greater than 10 raised to 14 ohms, which is used to measure the potential of the working electrode relative to the reference electrode. See video number E6. F. The potential stat which establishes the potential of the working electrode. How is the potential established in an industrial settings? Note: in industrial settings, electrode potential often arises from electrochemical reactions within the environment, not an external source. Analyzing this naturally occurring potential against a Pourbaix diagram allows for system state determination. This highlights the potential stat's utility in both control experiments and understanding real-world electrochemical processes despite the difference in how potential is established. Pourbaix diagrams lines A and B. Two parallel lines A and B are shown here. Equilibrium reactions for line A. H plus electron yields half a mole of hydrogen gas, valid for low pH values. H2O plus electron yields half a mole of hydrogen gas plus OH minus, valid for wide range of pH. Equilibrium reactions for line B. 2H2O yields O2 plus 4H plus 4 electrons. 4OH minus yields O2 plus 2H2O plus 4 electrons. Line A, line B. Line A. The area above line A indicates that water is thermodynamically stable. Within this region, any hydrogen gas present will be oxidized. This oxidation results in the formation of either hydrogen ions or proton or additional water molecules depending on the specific electrochemical conditions such as pH and potential. The area below line A, water is unstable and will decompose, producing hydrogen gas. Also, the equation of line A is E prime equals negative 0.059 times pH. Line B. Line B is related with the electrochemical equilibrium of water and oxygen. The equation is E prime equals positive 1.229 minus 0.059 times pH plus 0.015 times logarithm of oxygen pressure. Above line B, water is unstable and must be oxidized to give O2. Below line B, water is stable and the dissolved oxygen is reduced to H2O. Oxygen reduction reactions in neutral and acidic environments are correlated with each other. Video number E18 or slide number 237. Oxygen reduction in neutral environment, oxygen reduction in acidic environment. Water stability zone in the Pourbaix diagram. Here is the zone of oxygen stability, here is the zone of water stability, and here is the zone of hydrogen stability. Lines A and B are parallel and both have a slope of negative 0.059. The space between both these lines A and B corresponds to the zone of water stability. Therefore, upper zone H2O electrolytes analytically to oxygen gas. Lower zone H2O electrolytes cathodically to hydrogen gas. Middle zone H2O is stable and won't decompose. 3 regions in the Pourbaix diagrams. All Pourbaix diagrams feature 3 key regions. 1. Immunity region. 2. Corrosion region or regions. 3. Passivation region. The horizontal axis is pH and the vertical axis is potential, which reflects the oxidizing or reducing power of the environment. Increasing pH or decreasing proton concentration, increasing oxidizing power or increasing potential. An increase in pH signifies a decrease in hydrogen-ion concentration and vice versa. The immunity region typically found at the lower left of the diagram indicates conditions where the metal is thermodynamically stable and does not corrode. Immunity region is used for cathodic protection prediction, calculation, and intention. The corrosion regions represent conditions where the metal corrodes. The size of this region is determined by the metal's inherent thermodynamic tendency to corrode. Finally, passivation occurs when a protective layer forms on the metal's surface, preventing further corrosion. The area of the passivation region depends on the metal's ability to form and maintain this layer. Chapter 5, titled Active Passive Behavior of Metals and Alloys, is available to those interested. To find the videos more easily, please refer to the channel's playlist. Immunity region for prediction of cathodic protection of iron. This figure shows Pourbaix diagram for iron water system. Here is immunity region of iron. Hachures are shown in this figure. Corrosion by dissolution, corrosion by gasification, passivation by oxide or hydroxide layer, passivation by hydroxide layer, and immunity. Pourbaix diagram for the copper water system. Corrosion by dissolution, passivation by oxide or hydroxide layer, and immunity region of copper are shown here. More detailed Pourbaix diagram for copper water system or EPH diagram for copper is shown here. Immunity region, corrosion regions, passivation region, in accordance with the right figure. Challenge number 37. Thank you for your time and attention. If you like to challenge yourself, please answer this question in the comments below. Over what range of pH is nickel thermodynamically stable in deaerated water if the activity of Ni2+ equals 10 raised to -6? This figure shows Pourbaix diagram for the nickel water system. Here is immunity region, corrosion region, corrosion region, passivation region. This line shows the equilibrium between nickel and Ni2+ cation. Here the activity of Ni2+ equals 10 raised to -6.